Hello, are you ready to begin the next unit of calculus? I bet you are. Okay, so we've got one big unit left, and that is a unit that involves all kinds of advanced integration techniques, which is what we're starting today. Then we'll get into solving all kinds of differential equations. You've seen a little bit of it. You'll continue to see some more of it before we get to that section. And do lots of it. And then we also have something called slope fields. So that will be this chapter. This will be the last big full chapter you have. Then you'll see an additional few topics, and then we'll go into hardcore preparation for the AP exam or the CLEP exam if you're going to sit for one of those two major exams. So today we start advanced integration techniques. Now let's look at the three indefinite integrals on the left-hand side of the board. So I want to remind you that indefinite integrals mean antiderivatives. So on the first one, if I want to take the antiderivative of x to the fifth, I need to add an exponent and then say 1 divided by that new exponent. To do the antiderivative of 4x cubed, add the exponent, and then 4 divided by 4 is just 1. Here, and it wouldn't be plus, it would be minus. On the negative 6x, add the exponent to get 2, and then 6 divided by that 2 is 3. And then the square root of x is x to the 1/2, so when I add 1, I get 3 over 2, and then 1 over 3 over 2 is 2/3. And then don't forget the ever important c. That makes your answer the general solution. Okay? So remember, when you're doing the antiderivative of trig functions, I need to remember that the derivative of sine x gives you cosine x, and the derivative of positive 3 cosine x will deliver negative 3 sine x plus c. On this last one, remember, if I take the derivative of secant x, I get secant x tangent x. And if I take the derivative of x, I get 1 plus c. So guys, take a look at the 3 on the right-hand side of the board. Now, for instance, look at the antiderivative of tangent x. Well, I know if I take the derivative of tangent x, I get secant squared x. But what in the world do I take the derivative of that gives me tangent x? Wow, that's a much harder problem. And so are the two that follow. They're much more complicated looking than what you've done before. So we're going to get into a new method of integration, and it's going to be called u-substitution. And it's really a fancy pants way of changing our variables and turning a problem that looks too complicated to integrate into a simpler problem that is something we feel like we can integrate. So before we get started on doing u-substitution, let's review the chain rule. So I want to remind you, if you have a composite function f of g of x, to take the derivative of that, you say f prime of g of x times g prime of x. So if I want to take the derivative of this x squared quadratic to the 7th power, I'm going to have to say 7 times x squared plus 3x minus 10 to the 6th power. So that's my f prime of g of x. Now I need to do times g prime of x. So the derivative of the interior function is 2x plus 3. So we're going to have to really work at identifying the inside and the outside functions. Now, the big thing I know as a result of that is if I ask you to find the antiderivative of 7 times x squared plus 3x minus 10 to the 6th power times 2x plus 3, and then I have to have the dx on there because you can't have the indefinite integral symbol without its buddy dx at the end. I know the answer for that is x squared plus 3x minus 10 all to the 7th power. So you see that if I had given you the first problem, it would look pretty complicated to do the indefinite integral, but then the answer would turn out nice and simple. We're going to work on making that connection. All right, so on the second one, how do you take the derivative of e to the sine x? Well, what's the derivative of e to the anything? E to the anything, that doesn't change. But then you have to multiply by the derivative of the exponent, which is cosine x. I just realized over here I made a big mistake because I didn't add my plus c. I'm sorry. If you caught that, I probably owe you 2 bonus points on the most recent quiz, right? All right, so what I know as a result of my work on the left in the middle problem is that if I ask you to do the antiderivative of e to the sine x times cosine x dx, your answer is going to be e to the sine x plus c. So you probably, if you were to look at the indefinite integral problem, you might go, wow, how in the world would I do that? But hopefully by today's lesson, you'll have a gut feeling about how to get started and you're going to be able to flow through it. So on the last problem, to take the derivative of 6 times the square root of ln x, you may want to say that this is the derivative of 6 times ln of x all to the 1/2 power. You might think that that's easier to work with. So remember, that's going to be 6 times 1/2 times ln x to the negative 1/2 power, and then times the derivative of ln x. So what's that give us? Well, the 6 times the 1/2 gives us 3. And then on the bottom, I'm going to have the square root of ln x. And I'm also going to have an x on the bottom. I think it might be easier to put that there, and it might look nicer overall. So again, what that means is, guys, later today, if I ask you to find the antiderivative of 3 over x square root ln x dx, you hopefully will be able to come up with 6 times the square root of ln x plus c as an answer, okay? So you may think right now, oh my gosh, I could never do that. I'll bet you 10 bucks you can, okay? I have every confidence that you can. So, oh no, derivatives of arc trig functions, that's kind of difficult, right? Well, I know that the derivative of arctan x is 1 over x squared plus 1. So remember, you go 1 over not x squared, but x cubed squared plus 1. But then you also have to multiply by the derivative of the x cubed, which is 3x squared. So my final answer on this one, of course, would wind up being 3x squared over x to the 6th plus 1. Okay? So one more time, if I said, what is the antiderivative then of 3x squared over x to the 6th plus 1 dx? Later, probably not today, but later on in this chapter, hopefully you'll be able to work backward and realize that you've got arctan of x cubed plus c. So in general, guys, if I ask you to take the derivative of big F of g of x, you're going to say, well, that's big F prime of g of x times g prime of x. And remember, big F prime is little f of g of x times g prime of x. That means, in general, the rule that we're trying to get to is this whole idea of the antiderivative of f of g of x g prime of x. So I want you to go, wait a minute, f of g of x g prime of x, that, like if I take the derivative of f, capital F of g of x, that's what would give me f of g of x g prime of x. So we're trying to work backward to this composite function. And a composite function, remember, means one function nested in another, so f of g of x. Okay, So we're now going to do u-substitution to carry out integration problems, and that's just the opposite of using the chain rule for differentiation problems. All right, so let me just make a note, and these are sort of super simple problems, but I still want you to understand that right now, if I ask you to do the antiderivative of x to the fifth, you'd say, yeah, that's 1/5 x to the sixth plus c. All right, but if I ask you to do 7x plus 4 to the fifth, at this point, you don't know how to do that short of doing 7x plus 4 and multiplying that out, by itself 5 times in a row, which would be massive. But there's a real simple way to do that using u-substitution. So you can do the antiderivative of just sine x, but what about doing an antiderivative of sine of 3x, or the sine of x squared, or the sine of the square root of x, or the sine of cosine x? If you have anything after the sine other than just x, you don't currently know how to do it, but you will. That's what we're working on. You would know how to do the antiderivative of x to the 1/4. Well, you don't yet know, but you will know how to do the antiderivative of the fourth root of anything else. So we could do the fourth root of something simple like 2x minus 5, or the fourth root of sine x, or the fourth root of e to the x. We're going to be talking about all those kinds of problems where you've got functions that are a little bit just more than sine x or the fourth root of x or just e to the x. We know this. What if I make it e to some fancy exponent? What about e to the tangent x, or e to the x squared plus 6? If I make the exponent more than just x. Of course, you know that the antiderivative of 1 over x is ln of the absolute value of x. We don't know how to find the antiderivative if it's 1 over something more complicated. So anyway, I just want to make sure that you realize the difference is that you're going from a simple function like sine x to a composite function like maybe sine of 2x, or sine of x cubed, or sine of ln x, that we're putting one function inside another. So let me walk you through a couple of indefinite integrals and how I think through this, okay? So if I look at the antiderivative of x squared minus 9 all cubed times 2x dx, I'm looking for a part of this that looks like a composite function. And the part that looks like a composite function to me is y equals x squared minus 9 to the third power. That's the part that looks like a function inside a function, where the inside function would be x squared minus 9, and the outside function would be y equals x cubed. Now, I'm going to start out showing you some that are more obvious what the inside and outside function are. These get harder when recognizing the inside function becomes more challenging, or there's maybe 3 or 4 different ways you could do it, and you've got to figure out which way is right, and you only get better at that with practice. But guys, what you're going to do is set u equal to the inside function. So I'm just going to say let u be the x squared minus 9 part. Okay, so the game we're playing is to rewrite the integral so that you've got only u's and no x's. So at this point, what I've got is instead of x squared minus 9 cubed, I have u cubed. The problem is that I still have 2x dx. So I'm not ready to do anything because I can't have u's and x's in the same integral and proceed. So your next step is, once you establish your u, take the derivative with respect to x. So what is du dx? Well, it's 2x. And if you cross multiply, so to speak, you get du equals 2x dx. So watch, guys, this is the magic of u-substitution. I had u cubed, but I needed to replace 2x dx. Well, I've got 2x dx is du. Now my indefinite integral has nothing but u's, So we can integrate, and we can say, well, the antiderivative is 1/4 u to the 4th, and then plus c. Sorry, my pen's all of a sudden not writing where I mean for it to. But you want your answer in terms of x's, so I go back and say, well, that's 1/4 u to the 4th plus c. And remember, u to the 4th would be x squared minus 9 to the 4th. And there is your answer, guys. Isn't that cool? So I want to remind you that you can always check your answer, because now if you take the derivative of your answer, well, the derivative of 1/4 x squared minus 9 to the 4th using the chain rule would be 4 times 1/4, which is 1, x squared minus 9, drop it to the 3rd power, times the derivative of the inside, times the, or plus the derivative of c, and the derivative of a plane number is always 0. Well, that just gives you x squared minus 9 cubed times 2x. Guys, are you seeing that this answer corresponds to the integrand of the original problem, and that's how you know you're right, okay? So that also means that sometimes you all could go about one of these problems in two different ways, and both people be right, because when you took your answers and did the derivative, you got to the same final answer. And sometimes two people that do two different methods, their answers can look significantly different, but they're actually equal. You just have to do a fair amount of algebra to tell that. But if you do your derivatives and get back to the integrands, you can tell you're both right. All right, so on this one, again, let's look at what appears to be a composite function. Now, I could say, well, I've got x squared. That part doesn't really look like a composite function. But then when I look at the bottom, the 2x to the 3rd plus 1 all to the 7th, that does look like a composite function. So I'm going to say right now, I think my composite function is 2x cubed plus 1 all to the 7th power. And if that's true, then what I'm thinking is that the inside function should be 2x cubed plus 1, and the outside function should be x to the 7th. That would be how that worked if I asked you to do an f of g of x kind of problem. All right. Well, if I'm right, then my u should be the inside function part. So that brings me up to the point where we have the antiderivative of x squared over u to the 7th dx. That's where I am at this point. I'm not ready to go further because I'm not allowed to have x squared or x's and u's in the same problem. Hey, by the way, let me show you that it might help you to write that as 1 over u to the 7th times x squared dx. That might help you a little bit, okay? All right, so when I go back to u, let's do du dx. Well, du dx, if this is u, du dx would be 6x squared, and then, plus 0. So that means du is 6x squared dx. Okay, well, now wait a minute. I need to replace x squared dx. Oh, look right here. I could say that x squared dx equals 1/6 du. So I'm having to be a little more creative with how I substitute things in. But what I get is 1 over u to the 7th. And then the x squared dx becomes 1/6 du. Well, guys, this problem's doable because I've written everything in terms of u. But how could you write it to make it more antiderivative ready? Number one, if you're multiplying by a number like 1/6, it might help you to move it to the outside of the integral. And instead of saying 1 over u to the 7th, you might find it easier to do the antiderivative of u to the -7th. Now let's see what happens. We're going to get 1/6. We're going to say u, negative 7 plus 1 is negative 6. And then I'm going to divide by negative 6. And then I'm going to say plus c. So that's going to be negative 1/36. And u to the 6 is going to drop to the bottom plus c. So that's my answer in terms of u's. My structure is not great because you usually do these all vertical. But I tried to, with the prompts that I'm giving you to help you flow through the problem, I've got a little extra going on here. So my answer seems to be with x's, negative 1/36, u to the 6. What did we have for u? Oh, we set u equal to 2x cubed plus 1 plus c. Guys, let me mention that in a lot of these problems, you see how on the bottom there was a 2x cubed and on the top there was an x squared. A lot of times u will be the part with the higher exponent so that the du part contains the lower exponent. A lot of times that's sort of a trigger for how you set it up. All right, so let's check our answer. So to check our answer, we're going to do d dx of negative 1 over 36, 2x cubed plus 1 to the 6th plus c. Now, if I'm going to do that derivative, it might be better to write my problem in derivative ready form. So negative 136 times 2x cubed plus 1 to the negative 6th power plus c. I think that will be the easier way to do the derivative. So let's see here. When I drop the exponent, negative 6 times negative 136 is 1/6. And then it will be 2x cubed plus 1 to the negative 7th when I lower my exponent. And then the derivative of plus c. So let's, times the derivative of the inside, which is 3 times 2, which would be 6x squared. Okay, now wait a minute. That's going to wind up being 1/6 of 6x squared is just x squared. And then that's going to be 2x cubed plus 1 to the 7th. Hey, look. My answer when I was checking is equal to the original integrand. So that lets me know I did it right, okay? Now, I'm not going to go through all of these steps every single time, but I wanted to show you on at least a couple. So if you get yourself worked up in a jam, sometimes you might want to start doing the check work so you can tell yourself kind of where you're off or that you're actually right on track. Let's stop there so you can take a breather, and then we'll finish this.